Okay, let's move on. And we're moving on to problem number 10. The last was problem number 6. We're now doing problem number 10. And number 10 states the following. A 17-meter high, 11-meter long wall under construction has its bracings as shown in figure 932. The wall is in stable equilibrium without bracing, but it can pivot at its base. Calculate the force exerted by each of the 10 braces if a strong wind exerts a horizontal force of 650 newtons on each square meter of the wall. Assume that the net force from wind acts at a height halfway up the wall and all the braces exert equal force parallel to their lengths. Neglect the thickness of the wall. Okay, so basically you have a wall that's 17 meters by 11 meters, and it is braced up by a series of 10 braces, that each of which, and these braces are all at a 35-degree angle at this point. And so it's saying that the braces, the horizontal component of that is going to be what is important in terms of holding back the wind. Now, by itself, without the wind, this thing is balanced, but it can pivot at its base. Now that's important because otherwise you'd have to take the weight of the wall into account. And here's the wind force. And the wind force is going to equal 650 newtons per square meter. So basically that tells you, in order to figure out what the total force is, you're going to have to multiply that by the area of the wall. And the area of the wall, so it's going to be 650 newtons per square meter, and the area of the wall is going to equal 17 times 11, and that's going to be square meters. So the total force is 650 times 17 times 11. And if you do the calculation here, you get 1.2 times 10 to the 5th newtons. And that's the force of the wind here. Now, the wind causes a pivoting around, so 8.5 is how high this force is. That's this distance right here. So 8.5 times 1.2 times 10 to the 5th is the torque exerted by the wind. And this is balanced by the 10 braces times whatever force each brace is exerting times the cosine of this angle theta, because the cosine is this parallel component, and it's going to be the cosine of 35 degrees. And so if you rearrange this and do the math, you get 1.50 times 10 to the 4th newtons per brace. And that's each force per brace. The next problem is problem number 12. Now in problem number 12, all of the problems up to this point have only taken into account the torque. Starting with problem number 12 and problem number 13, we also have to take into account the first law of equilibrium, was that the weight has to be balanced. Remember, the total weight, which means the downward weight and the upward force, have to be equal and have to be zero. The sum of those have to be zero. And so this is the first problem that you have to take that into account. So let's read it. Suppose the weight of a drawbridge drawn in figure 934 is supported entirely by its hinges and the opposite shore. So let's draw that down. You got hinges here, opposite shore here. You've got a wire that goes out like this. And it's got in the diagram, it's got an F here. That is not the same as the F that we're going to be talking about in just a minute. So in this diagram, you have the weight of the drawbridge, which is a downward, and the drawbridge weighs 2,500 kilograms. And that is counterbalanced by the force up at the hinges and the force up at the opposite shore. Now I'm going to say that this force at the hinges, we can call that the normal force, and then we can call the force at OS normal, and we can call this other one F, the force at the hinges. And for this first part of this problem, the assumption is that this is directly perpendicular. And that's the way this first part it reads. It says, what is the weight supported by the opposite shore if the point of support is directly beneath the cable attachments? And so you have the force here and the force here upward and against the weight downward. And so that means that F has to equal N plus, or F plus N has to equal, let me change that. F plus N has to equal the weight. Also, however, 9, the distance from the hinges to this thing, the second equation, 9 times F has to equal 7.5 times the weight. The weight is right here, by the way. And this distance here is 7.5, and the total distance is 9.0. So you have 2 equations and 2 unknowns. So F is going to equal 7.5 over 9 times W. If you multiply that, F equals 2,400 newtons. And then N is going to equal the total mass, 9.8 times 2,500 minus 2,400, which is going to equal 4,080. So the mass at this point, which is being called N here, and the force here, these are the 2 forces. So the question is, what percentage of the weight is held up at this point here? So you'd put 4,080 and divide that by 2,500 times 9.8, and you get 0.16333, or just put 0.16. Now the other thing you could do, if you notice this ratio right here, the other way you could have done it is calculated that, and that would have told you that 8.83 or 6, etc., is being held up by this force, and so the rest is being held up by the hinges. Now the second part says, what is the direction and magnitude of the force the hinges exert on the bridge under these circumstances? And it's going to be this value, 2,400 newtons straight up. Number 13 uses the same diagram and just tells you that now there's a car on this bridge. And the presence of the car on the bridge changes everything. If you were to draw I'm not going to redraw the diagram, but redraw or draw a free body diagram, at the point, if you take the bridge as a whole, you have the force of the normal, which is designated F. Now, the reason that this is all different is now the cables are taken into account. Previously, the cables were slack, which is why the angle of the F was 90 degrees. The cables were slack. But now, because the cables are no longer slack, the angle F is no longer 90 degrees. And so you have two forces upward. You have basically the T component, the tension, its Y component, so Ty, and you have the Y component of the Fy. So those are the two upward forces. The downward forces are the weight of the bridge and the weight of the car. And so those are the two downward forces. And so if you were to, the weight of the bridge is going to equal 2,500 times 9.8, which is equal to 2.45 times 10 to the fourth. Can't read my own handwriting. And the weight of the car is going to equal 900 times 9.8, and that's going to equal 8.8 times 10 to the third. So Fx, that's this force here, the x component of this force is going to equal F cosine theta, where theta is unknown, and Yx, or Fy, is going to equal F sine theta. Again, theta is the unknown, and it's designated theta in the diagram in the book. And so we know that Fx has to counterbalance the, now Fx is in the horizontal plane, okay? The bridges and the cars are not moving this way, and so this Fx has to counterbalance the x component of t. So it's t, and the x component of t is cosine 40 degrees. And we also know that Fy equals Fw plus Fc, so the car, but it minus Ty, where Ty is T sine theta, or 40 degrees, excuse me. So we have our two equations and our two unknowns. Our unknown is T in this case, and then up here, theta is our other unknown. And so we can then write the net torque as follows. The force of the bridge times 1.5 plus the force of the car times 3.75, because the car is halfway across the bridge, has to equal the y component of the tension times its distance, which is 9. Now here are your two equations. This set and this one. And so you can use one of these and find a value and put it into the other one. And so what this means, so if I took this one, because if you look at this equation, there's only one unknown, and that's t. So we put in 2.45 times 10 to the fourth, times 1.5 plus 8.8 times 10 to the third times 3.75. That's going to equal t times the sine of 40 degrees times 9. One unknown, t. If you do the calculation here, t comes out to equal 1.21 times 10 to the fourth. I can't read my handwriting. Now we use that value for t. We say that f cosine theta is equal to t, which is now we know, times the cosine of 40 degrees, the x component of f. And if we calculate that, f is going to equal 9270 divided by the cosine of theta. We do the calculation and we get theta is equal to 70.1 degrees. We know 70.1 degrees. We also know that f is equal to 9270 divided by the cosine of the theta we just found, and that's going to equal 2.72 times 10 to the fourth newtons. So we found the tension, theta, and the force. We actually had three unknowns, but in this equation, we found the first one, and then we used this equation and this equation to find the other two.